sequence. So we have this answer to this question, so how much information does a network produce? But what we're interested in is a slightly but sort of subtly different question, which is how much information does a network convey to a human observer? Or another way of putting that is how much information does a human perceive from a network? And it turns out that the answer is a very simple generalization of entropy. It's simply the cross entropy. So instead of minus log Pij, what we have is minus log P hat ij. So this is the amount of information that a stimulus conveys to a human with some expectations P hat. And again, you just average over the sequence. So now you can see that we needed to answer the first question before we can even start to answer this question. We need to know what, we need to at least have a model of what P hat is before we can start to quantify this quantity. How much information does a network convey to a human? So this is the quantity that we're going to be interested in. We're going to see what happens in different kinds of networks. So one last little bit of mathematical help. I think it helps to gain a little bit of intuition by looking at this simple equation. And this is like one of my favorite simple equations. So if we have this cross entropy, which is just minus log P hat, and again we just think of it as perceived information, the amount of information a human perceives. You can really easily break it down into the entropy, or the amount of information that the network is producing, plus this extra term. And this extra term is known as a KL divergence between P and P hat. And it's simply, in very simple words, you can think of it as just the difference, in a sense, or the distance between P and P hat. So if P and P hat are equal, which would mean that the person has an exact representation in their head, then this term is 0, and then they simply perceive as much information as is being produced by the network. But if P hat doesn't equal P, which we've seen in our human experiments, then this term can only be, it's never negative, it can only be 0 if P and P hat are equal, or positive if they're different, because it's like a distance. So if P hat doesn't equal P, then this becomes positive, and then people are perceiving more information than is actually being produced by the network. And in this way, you can think of this extra term as inefficiency. It's the extra amount of information that people are having to process because their estimates in their head are inaccurate, because they have inaccuracies in their expectations. So we have perceived information equals produced information plus this inefficiency, which I think is super helpful just for sort of intuition. So now we can go and look at some real networks and see what do these quantities look like in real networks that we find in the real world. So let's take, what we did is we took a ton of networks. I think we have 40 here. And the only criterion that we considered when picking all these networks was just that they have some interpretation as communicating information to humans through sequences of items. So we already spoke about word transition. So here we took some famous texts and we parsed them and then took all the words in the text and then made networks of transitions from one word to the other. So I showed you a picture of the Shakespeare one. We also looked at semantic relationships instead of just transitions. So you can look at a thesaurus, for instance, as one example, and you say if this word is listed as a synonym of some other word, then you make an edge. And in this way, you have a network of sort of the relationships, the meaningful relationships between words. We also look at web hyperlinks. And the sequence here would represent sort of surfing the internet. So when you're surfing the internet, you could imagine sort of randomly clicking on hyperlinks and you're doing a random walk in the network of the internet. And you do a similar thing when you're searching through citations in science. And in social networks, and then also in music we spoke about. So we took a bunch of different sort of famous songs and took the notes from those songs and then looked at what sort of notes transition to other notes in the songs. And I had fun for like a week looking at all the information properties of Queen was the most complex. I can tell you that one. It was kind of fun. And Africa by Toto was the simplest. So we have these 40 networks, and the only thing connecting them is that they're sort of, you might expect them to be designed in some way, or not designed, they might have evolved over time to communicate information to humans. And we can imagine remember those two quantities. So we had produced information and then we had the inefficiency. And so we can look at what both those two different quantities are in these real networks. So here, let's first focus on produced information, or just the entropy of random walks on these networks. So what I'm plotting here is on the y-axis, I'm plotting the entropy of the network, of the real network. And then what we do is for each network, we take it and we randomize its structure. So we just generate a random network with the same number of nodes and edges. And then we calculate the same thing. How much information is this random network producing? And what we find is that all of our networks lie above this x equals y line. So for every network, it's producing more information than you would expect if it was just a randomly organized network. So something about the structure of these networks is allowing them to produce more information than just a random network would have. And now we can ask the same question, but for this inefficiency question. So again, on the y-axis, what we're plotting is the KL divergence, or the inefficiency of these networks when they're communicating with humans. And on the x-axis, what we're plotting is sort of the inefficiency of an equivalent randomized network, again. And what we find here is we find the exact opposite result, that all of these networks lie below this x equals y line here. Which means that, again, there's something about the structure of these networks that allows them to communicate information to humans more efficiently than a random network would have. So something about these network structures is giving them two interesting properties. They're producing a lot of information on the left, but they're also communicating efficiently with humans on the right. They have a low inefficiency. People are able to build an accurate representation in their head of these networks. So now you might ask, so we see these information properties, so you could ask, well, what is it about the structure of these networks that's giving rise to these two properties? So we've talked about information, but what really do these networks look like that's making them have these properties? So we'll take entropy first, so produced information. And it turns out that for a network to produce a lot of information, it turns out that the key property to look at is the heterogeneity of the network. So I'll define what that means. So a heterogeneous network is one where the degrees, which we've talked about before, so the degree of a node is just the number of connections that it has. In a heterogeneous network, there's a big spread in the degrees that nodes have. So some nodes have very low degree. So for instance, this guy has a degree of 1. These have degree 2. And then you have some with degree 3, like this guy. But then you have this big hub node with degree, I think I counted on the train, I'm pretty sure it's 11. So you have this big spread in the amount of connectedness that nodes have. And again, these heterogeneous networks are characterized by the presence of these hub nodes. And in the English language, as an example, you can think of a hub node as a word that shows up a lot and connects a lot of other words. So like the word be or the word to shows up all the time and is connecting other parts of speech. And you can think of analogous examples of hub nodes in all the other networks that we looked at. So in the internet, you see it in social networks a lot, for example. Like, so you have people that are very well connected in a social network or have many followers on Instagram or something. And then there's many, many more people that only have like 100 followers or something. So many networks that we see in the real world have this heterogeneous structure. And so what we can do is we can generate a bunch of different networks with varying degrees of heterogeneity, or varying degrees of this spread in their degrees. So that's on the x-axis. And on the y-axis, we can just calculate how much information is being produced by these different networks. And what we find is a trend like this. So you can look at networks with very low heterogeneity. So the clearest example is a lattice graph. So in a lattice network, all the nodes have exactly the same degree. Just imagine, I should have drawn periodic boundary conditions, but imagine that this node connects to more in both directions. Every node in this graph would then have 4 connections, and so it has the lowest heterogeneity you could have. In fact, it's completely homogeneous. And then we find that these networks produce the least information. Then you could imagine a random network that is slightly more heterogeneous and therefore produces slightly more information. And then you could look at networks with a lot of heterogeneity, these hub nodes that are connected to almost everyone in the network. And these are producing the most information. So the upshot here is that we see that heterogeneous networks are producing more information. Mm-hmm.
I was just curious, do the edges, does the size of the edges have any impact, or is that just like what the computer said?
That's a good question. So all of this does change if you include edge weights, which I haven't spoken about at all. So you could have different weights on different edges. Here I'm just assuming that all the weights are the same. If you see any differences in weights, it's just completely erroneous. It's just from me not plotting it correctly. But you could imagine, you could ask all these questions again with edge weights and you get interesting things. But a similar intuition holds as you see here. So now we can look at that second property. So we saw that all the real networks that we looked at were efficient relative to random networks. And it turns out that the key to understanding efficient communication with humans is modular structure or community structure. So here's an example of a network with high community structure. Or you could also say it has high clustering. And when we say high clustering or community structure, what we mean is that there exist clumps or clusters of nodes that are very tightly connected with one another, and then there's sparse connectivity between the clusters. So we see that there are sort of 4 clusters here, this guy, this guy, this guy, and this guy. And within each one, if you just focus on, say, this cluster, there's strong connectivity between all these nodes, but then they're weakly connected to the other clusters. And you would say that this network is highly clustered. And this is another property that is almost ubiquitous in networks in the real world. So social networks, again, is a really good example. So you form cliques with your friends, and then you have sparse connectivity to sort of other friend groups. So you see this a lot in social networks. You also see it in languages. So words tend to form clusters. So if I say the word dog, then immediately what comes to mind are other closely related words like cat or food or walk or leash. And in the same way, linguists now know that almost every language that humans speak are very highly clustered like this. And so we can do a similar thing to what we did before. So we can look at networks with varying degrees of clustering on the x-axis, and then we can look at this inefficiency term on the y-axis. And again, sort of the least clustered types of networks are these lattice networks. So there's no community structure here. There's no like natural grouping of these nodes. And you can actually show that gives rise to high inefficiency because people are good at grouping things together. So when there's no natural grouping, it's hard for them to anticipate what's coming next. And then you can look at random networks again, and these are slightly more clustered and therefore have slightly lower inefficiency. And then you can look at these very clustered networks, and they're the most efficient. They have the lowest inefficiency in terms of communicating information to humans. So that was the last little thing I wanted to talk about. So just to conclude, we sort of looked at 2 different aspects of how humans interact with networks. We looked at how humans learn networks, and we saw that errors in humans learning in a large way impact our sort of anticipation of events and impact what our sort of internal representation of what these networks look like. And then we sort of flipped the script and asked what types of networks are able to communicate information both rapidly and efficiently to a human observer. And we saw that real networks actually are organized in a very specific way to have both of those properties. And so some of the sort of future directions that I have been thinking about with some of the people that I work with there's many different directions you could take, but some natural ones are, so from a linguistics perspective, we see that a lot of these, linguistics, but also, many different perspectives. But we see that these real networks have these 2 interesting properties. So is it the case that these networks have always had these properties, or did it evolve over time? So you can imagine looking at like Old English and asking, was it less efficient at communicating than English today? Or is slang somehow allowing us to communicate more efficiently or produce more information? So that would be sort of the first question. And then you could also imagine attacking this from an engineering perspective and saying, if I wanted to design a network to optimally produce a lot of information, but be very efficient in communicating with humans, what would that network look like? It would presumably be very heterogeneous, but also very clustered. And could we use that to communicate better? Like if I had designed, in this talk, I had a network of ideas that I was trying to convey to you, and I had to pick a linear sequence to convey those ideas, could I have sort of optimized the order in which I presented these ideas to you to most efficiently and most rapidly communicate the information? So that's sort of an engineering type question. And so I just want to thank the people that I've been working with, and thanks to Genji and the Entropy Theoretical Neuroscience Club. I think it's really cool. And if you're interested, these are a few of the papers that I've been working on. 2 are about to come out, hopefully in the next month or so. So if you're interested, they're up online in various places. So thanks.
Can you go back to the slides I just put before? So in the beginning, you talked about how, like, the map from Shakespeare was that was connecting words, like, in the sentences he wrote, right?
Yeah,
But
yeah.
then this is implying more that we might, in our minds, map words by meaning, or a thesaurus, or a, like, dictionary word.
Yeah, I think if I could be wrong, but I think that in linguistics, the hypothesis right now is that people sort of at 2 levels of connect, like they're doing both at once almost. Like they're anticipating what's coming next, but then they have a different map in their head of the network of meanings of words. And there's an interaction between those 2. Like you are likely to see words that are related in meaning closer together, but it could be the case that like the word "the" isn't particularly meaningfully related to a lot of words, but it is very close in terms of transitions. So we think that humans are actually kind of doing both at the same time. And understanding that interaction actually between meaning and just pure transitions between words is something that at least one kid in my lab is trying to think about. And I know other people are trying to think about that. It's a good question. Mm-hmm.
Is he just looking at meaning, or is he also looking at, well, okay, never mind, I was going to say syntax, but that's the opposite question.
Yeah, no. Well, he's trying to look at both at the same time. So you can design then. So you get to pick, so imagine you're running one of these experiments. You can pick the network used to generate the sequence. So that is sort of like the syntax. It's sort of like picking the order of the words. But then you can, as the stimuli, you can choose what words to assign to each node. So for instance, in this network, you could imagine doing 2 different experiments. One where we have the structure aligned with the semantics. So you could have these words all actually mean the same thing. So have 4 clusters of words that are related by meaning but also structure, and see what happens there. Or you could do something else where you have them related in the structural sense, so they're going to appear close to each other in the sequence. But maybe you only include in the same cluster things that are very different in terms of meaning. And he wants to see if you can detect differences in people's behavior between those sort of 2 cases.
Is he at all using ERP studies, or like?
He's using WordDevec, so which is basically like a way of taking a word and placing it in some high-dimensional space. So then you can have like a distance metric between the meanings of words, sort of. Like queen. There's this is actually really cool. There's some really famous result. So your WordDevec basically takes a word and makes it every word like some 100-dimensional vector with different properties. And then you can do math with words, which is really fun. So it turns out that king is equal to like queen minus woman or something. Or minus man plus woman. I think, yeah. Queen equals king minus man plus woman. Like you can do like these funny like math things, which is kind of cool.
Thank you, by the way.
No problem.
I'm just confused about one thing.
Yeah.
Why is it that in the heterogeneity means more information? Well, what do you mean when you say entropy means like is more information?
Yeah.
I don't know.
That is at the heart of. That's a very good question, and that is a question that people are still grappling with and have been grappling with from like the beginning of information theory. So there's a sense in which when I say and what Shannon meant when he wrote down entropy means information, or my interpretation of what he meant, is that it's sort of surprising you. You can think of it as surprisal. So for example, if I tell you something and my word is gospel, I'm not going to like lie to you or anything. So if I tell you something, and it's something that you wouldn't have expected before, that conveys a lot of information to you. So if I surprise you, then it's going to convey a lot of information. Whereas if I tell you the sun's going to come up tomorrow, you already expected that with like 0.9999% probability. So that conveys almost no information. You're not surprised at all. So it literally means surprisal in a sense. You're on average surprised by what you're seeing. And then you can ask whether or not that actually means information in the sense that we mean it. But I would argue that in some cases it does. So in this case, like if I tell you something that you don't expect, then that's going to convey information. But there's also other senses in which it doesn't tell you like what kind of information I'm telling you about. And it does depend on the context. So it does become tricky. And that's actually an open area of research, is trying to think more about like the semantics of information, like the meaning.
I have one more question.
Mm-hmm.
So are networks like, can networks change over time and like get new nodes and like
Yeah,
shrink or-
yeah. Networks are constantly like shifting and changing. So like the English language is constantly shifting. We're constantly adding words, and the way people speak is constantly shifting. But social networks are constantly shifting. Like you add friends on Facebook, or get new followers on Instagram or something, lose others. These networks are all inherently dynamical, which is also interesting. So you could see that's sort of like that first question that I'm interested in answering. Which is like, so if you watch these networks evolve over time, how are these properties changing? Are they becoming more efficient, less efficient? I think there's a lot of interesting questions there. Mm-hmm.
Sorry. So for processing information, can I see it as a parallel to like the way we perceive images, and because of the fact that they're so structured in a lattice, we can sort of encode like repetitions as zeros and then like surprisals as ones, and then the sparse zeros would just be condensed. And so when we reconstruct the information, we don't have to include so much repetitions.
Exactly. And so the word condensed, that's actually another, I should have added that as another direction. But that is exactly what we think is going on, is that networks that are more compressible in an information theoretic sense or in a computer science sense, we think people are basically trying to learn compressed versions of these networks. So we see that these modular networks, so these networks are more efficient. And what we think is going on is exactly like what you're saying, is that people are sort of learning compressed versions. So they're like grouping all of these together, and grouping all these, and grouping all these, and grouping all these. So they have this really simple representation where they have like 3 or 4 supernodes connected. So, and it's much more compressible than like a lattice, where there's no natural way of grouping these nodes and compressing the description of that network. So that's exactly what we think people are doing, is trying to compress their description of the network. That's a really good question. Mm-hmm.
So I have 2 questions. So one is, a lot of these measures seem very similar to measures that people use to analyze like brain networks
Mm-hmm.
in the brain.
Yeah.
Have you seen anybody sort of relate the structure of networks in the brain to these preferences that you detect when people are trying to learn abstract networks? Like sort of
Mm-hmm.
maybe a correspondence that the brain is highly clustered and therefore we prefer to like it's easier to encode clusters in abstract networks.
That's an interesting question. And my advisor is definitely trying to make that link between structures in the brain and structures that we see external to us.
Sure.
I haven't clarified it in my head. The one thing I will say though is that we definitely see relationships between people's patterns of neural activity and these network effects. So one of the very first papers that showed that people are surprised by these cross cluster transitions, they actually had the people in fMRI scanners, and you can see literally in their brain, their representations of these networks look different when they cross a cluster versus go within a cluster. So literally in their brain, the firing patterns look different. And that paper is really cool. I can point you to that paper if you want. That was the paper that sort of kickstarted actually a lot of this work. She's also at Penn. It's actually a new faculty member at Penn, just joined this year. In case, her name's Anna Shapiro. So I can, yeah, I'll show you that paper. It's really cool.
Cool. Sorry, 1 second
Mhm.
question. So I feel like the underlying idea here is also that we learn these, we're exposed to these sequences, and we sort of try to infer the network structure, and then we build up this representation of the network.
Mm-hmm.
But for any given sequence, there's many networks that I could infer from it, right? I could go from just transition probabilities, or I could build a semantic network, or how do you choose the network that you're comparing their responses to?
That's a good question. So we pick the networks in our experiments to try to elicit a certain, or try to probe a certain behavioral response. So that clustered network, I wonder how far I have to go back to find it. Probably pretty far, so I'm not going to do it. Actually, I have some extra slides.
Oh, there's a lot.
This is all extra stuff.
You're hiding a lot of stuff.
This is just extra slides that I presented before, so I threw it at the end. But I'd have to go. So you remember that one that has the 3 groups of 5 nodes. So that one has been picked because it is in a sense maximally structured, given that you have, if you want to only look at nodes of a certain size. So we look at small networks first of all, because it's easier to do actual human experiments with them. And then we picked it because it was very structured, so you could clearly see the difference between a cross-cluster edge and a within-cluster edge, and then you can ask whether or not there's some behavioral difference or a difference in the brain. So that's why that network's been chosen. But then there's depending on the question that you have, you might pick other networks. So for example, I didn't talk about these results, and I won't get into it, but we ended up looking at this network, which is like a ring. So everywhere around this circle, each node is connected to its nearest neighbors and next nearest neighbors. And this network has the exact same properties, or the main property that we were looking at before. So all of them have 4 connections, so you can convince yourself. So they're all just connected to their neighbors and then the 2 hops away. So they all still have 4 connections. And here what we were interested in seeing is if you throw in a random sort of violation of the structure. So suppose they're hopping around this network. They go here, here, and then back around. And then you throw in something completely different that breaks the network, that breaks the structure that they've been seeing. So maybe they're here, and we send them all the way to here. Then you can see what sort of behavior is elicited. And so for that question, we wanted to know if you send them farther away in the network, is that different than sending them closer, even though they've never seen either of those transitions before? And to ask that question, we wanted to look at this network because it's clear to see what far and close means. So if you have this white node, this would be far, like one of these red nodes would be far. Blue would be kind of closer, but still not allowed. Like there's no connection between the white and the blue. So it's a violation of the network, but it's closer than the red ones. And you can see that people are actually more surprised when you go all the way across the network than if you go a little bit closer, which makes sense intuitively, but when you think about the fact that they haven't seen any of them, it's like, why were you even anticipating one more than the other? It's kind of interesting. So it just depends on the type of question that you want to ask, if that answers your question.
This is a question about the modular one at the beginning in the experiment.
Yeah.
So for the experiment, was it like they looked at that picture and it was like a dot moving around?
So that's a good, so yeah, I can actually quickly describe what the experiment was. So the person is sitting at a computer, and this is their hand is on the keyboard like this.
Yeah.
And all they see is one row of gray squares. So imagine this all isn't here and you just see this row. And at the very beginning of the experiment, you just see 5 gray squares in a row. And then 1 or 2 of the squares will light up red. So in the first stimulus, say this rightmost square lights up red. And that just means press your pinky. Then once you do that, it'll transition to the next one. And say the next one is this square and this square light up. And that just means press your thumb and your middle finger. So all they see is just like 5 squares that are usually gray, and then 1 or 2 of them will light up red. So they never actually get to see the network as a whole.
Okay. And so like each
So each
combination
each like one of these
okay.
stimuli, we'll call this a stimulus, like this row, is assigned to some node in the network. And then we randomly hop between those nodes, and that's how we determine the order of the stimuli.
And do you like randomly assign them as nodes to the network?
Exactly, yeah. So you want to make sure that the stimuli, like obviously it's harder to press your thumb and your ring finger down than just pressing your pointy finger down. And so that will give rise to an increase in reaction time. So to make sure, exactly like what you're saying, to make sure that the effects aren't just being driven by people having trouble pressing the buttons, you randomize, the assignment of the stimuli to the nodes in the network. It's a good question. Do you have a question? No? Mm-hmm.
So when we had this is so cool.
Nice.
But when we had the ring with the jumps every 2, but
Yeah.
also to the next one, what happens to that graph we were looking at that said sometimes you swap the order of
Mm-hmm.
where they should be? Because if you swap 2 that are next to each other, nothing happens really.
Yeah.
And like if I see the white one and I give you the wrong green one
Yeah.
because I swapped the 2 on either side of it,
Yeah. That's
I
actually.
could be wrong, but I'm right also. So.
Yeah, no, that's actually the key. That's actually the key to the whole, so you asked about compressibility, and that's one way of thinking about it. But the way that I first originally started thinking about it is exactly that way. So if we look at, I should just, I guess I don't. Let me just click. Let's go back. I just want to show you this. Okay, so now we can go back to this original network. So the exact same property happens in this network a lot. So imagine there's a sequence. It goes here, 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 let's say. If you mix up the order in your head, so it actually went here, 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 but in your head you remember here, 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 let's say, so you just mix up these 2, then you're still reinforcing this edge and this edge, even though you never actually saw this transition. You're still, exactly like what you said, your memory's mixed up, but you still reinforce a correct edge. And that's why we think this clustering helps. So triangles are really important. Because if you mix up just one and there's a triangle, you still are reinforcing an actual edge, even though you did so by complete accident.
So
Yeah.
shoddy memory, or like that error in
Yeah.
memory just happens to help you. So that maybe
Yeah.
when you do see it, it's sort of already reinforced.
Exactly. Or another way of thinking about it is from the network perspective, these types of networks help people to correct for their own mistakes. So this network, just through its organization, having a lot of these triangles, is helping people immediately by accident correct for their own errors when they're in their memory. So that's exactly how I think about it. Whereas a lattice, if you remember the lattice with the squares, doesn't have that property. If you mix up 2 for any sequence, you're gonna make a mistake in adding an edge between nodes that doesn't actually exist. That's exactly the intuition. Well, thanks y'all for coming.
Thank you very much.
Yeah, no problem. God, how much fun it is to talk to Swatis. Y'all got this so much faster than most of the people in my lab.
Grad student.